Hey everyone, we are going to do the second problem here from section 5.3 on average value of a function. So we are going to be finding the average value of f of x equals 2x squared on the interval from -1 to +1. And so remember our formula that we're using for this, average value of f, is determined by doing the integral of f from a to b, so of f of x dx, and then dividing by the length of that interval, b minus a. So in our case here, our problem is going to look like the integral from -1 to +1 of 2x squared dx divided by 1 minus -1. Okay, and then if we simplify that a little more, we could see that we are dividing by 2 down here. So we could also just write this as 1/2 times that integral. Okay, so divide by 2, same as multiply by 1/2. All right, so we are going to need to figure out what the value of this integral is going to be. And that's the part that's going to take a little time right now, because the only way we have so far to do this is to use the Riemann sum definition. And from what you saw in our last class, that does take a little while. So let's take a look at that. All right, so we are going to find this value right here. Okay, so let's write down our Riemann sum definition for the integral. 1 to 1, 2x squared dx. Okay, this is the limit as n goes to infinity of our Riemann sum. K equals 1 to n f of ck times delta x. Okay, so yeah, just to recap from last time, remember that a Riemann sum is where we're adding up the areas of a bunch of little rectangles, okay, just like we were doing in section 5.1. Delta x is the width of those rectangles, and then f of ck is the height of each rectangle. So ck is going to be, the default setting is the right endpoint of that rectangle. And we'll see how to calculate all of those pieces here. Okay, so if you remember our other Riemann sum integral problem, we broke things down step by step so that things could build on each other and you're just focusing on one thing at a time. So we're going to do that same process here. All right, the first thing that we're going to start with, kind of where it all hinges from, is in finding delta x. Okay, and remember we are saying that we're going to cut our interval up into n equally sized rectangles, and our formula for delta x is then going to be b minus a divided by n. That gives us the width of each little rectangle there. All right, and so we plug in our limits, b and a. And remember that n right now is just like some constant number of rectangles. For the sum's purposes, it's just like however many rectangles you had. So we're going to leave that n in there because eventually we're going to let n go to infinity. So we're just going to leave that sitting right in the expression. And so we're going to get 2 over n for our delta x term. Okay. Now the next thing that we want to find are those ck points. Okay, so find your ck's. And remember that those are the right endpoints of each rectangle. And we saw in section, what was that, 5.2, how we would derive this formula for the right endpoints, but we figured out that it was a pattern that looked like a plus k times delta x. Okay, and so we're going to plug in our a value, -1. K is our index on summation, so we want to leave that k right there. Okay. And then delta x we just found was 2 over n. So we're going to multiply by that, and we'll end up with -1 plus 2k over n. Or you could write that as 2k over n minus 1, either way. I'll just leave it like that. Well, no, it might be easier if we did the subtraction. Okay. Yeah, sure. Let's do that. Okay, 2k over n minus 1. All right. Now that we've found ck, that means we can find f of ck. All right. So that is step 3. Find the formula for f of ck. All right. And here we can see that our f of x, our function that is being integrated, is 2x squared. Okay. So when we do f of ck, that's going to be f of the formula that we just found for ck, 2k over n minus 1. And so when we plug that into our function, that's going to be 2k over n minus 1 squared. Okay, just putting it in for x right here. All right. And so we're going to need to do some distribution there. Let's see what we've really got. Okay, so we've got the 2 out front, and then distributing those terms, you'd multiply by another 2k over n minus 1. That'd give you 4k squared over n squared minus 2k over n minus another 2k over n. So that would be minus 4k over n plus 1. Okay. And we could distribute that to n or not. Let's just leave it right there for right now. Okay, so that's f of ck. Okay. Now we've gotten all the pieces for our sum. We have ck, and so we have f of ck. That's good. And then we also have delta x, and so we can set up our sum now, and that is step 4. Set up the sum. Okay, so the integral here, -1 to 1, 2x squared dx, is going to equal the limit as n goes to infinity of the summation, k equals 1 to n, and now we're just going to put in the things that we found for f of ck and for delta x. So here's f of ck, k squared over n squared minus 4k over n plus 1, and then delta x was 2 over n. Okay. So that's the basic setup of what we're going to need to evaluate here. We're going to need to evaluate this sum and then take the limit as n goes to infinity. And so that's what we're going to do next. All right, and you know this is the big one. This is where we do most of the work, is in evaluating the sum and limit. Okay. So let's take a look at this. Let me write down what we're doing here. Limit n goes to infinity of our summation, oops, k equals 1 to n, 2 times 4k squared over n squared minus 4k over n plus 1 times 2 over n. Whew. Okay. All right. So the first thing that we're going to do here is we're going to look to use our algebra of finite sums. So remember from section 5.2, we want to make use of these three rules: the constant multiple rule, sum and difference rule, and the constant value rule. So our summation looks a lot like this type of thing, summation from k equals 1 to n, and we're going to see how we can break things down and put these three rules to good use. Okay, so the first thing we're going to look for, usually this can happen right off the bat with these Riemann sum integral problems, is there's usually some constants hanging around inside the summation, some constant multipliers. So let's go see if we have some terms like that. Okay, so we lost our spot here a little bit. Okay, here we go. Yeah, we're looking for constants inside this summation. We can see one really clearly here. There's a 2. We're going to be able to pull that out of the sum. Okay. But then the other one, like we saw the other day, is going to be this 2 over n right here. All right. And that does feel a little funny at first sometimes, because you tend to think of n as being like a variable type of thing. But remember that when we're looking at our summation here, k is really the only thing that's changing at that time. That's our index, where we're starting with k equals 1, and we get our term, and then we change it to k equals 2, and we get our term, k equals 3, etc. N up here is just a value giving you your stopping point. So in the terms of the sum portion, n is effectively a constant. Now that's going to change when we look at the limit, because with the limit, n is actually going to not be a constant. We're going to let n go to infinity. So we want to watch out for that. But right now, we're just focusing on the summation part, and n is going to act like a constant at that time. So we're going to be able to pull our 2 and our 2 over n out of the summation here. So here's our limit still, 2 times 2 over n pulled out of the summation. Okay, 4k squared over n squared minus 4k over n plus 1. All right, so that's a good place to start. Now notice that inside our summation, we have sums and differences, a sum and a difference. Here's a sum, here's a difference of different terms. So we're going to be able to use our sum and difference rule from section 5.2. And we're going to be able to separate this part into 3 different summations, one for each of those terms. All right, so that's our next step. Still got our limits. Our 2 times 2 over n, we can stick those together, call that 4 over n. And then set yourself up some nice big brackets here to hold our 3 sums. First one, sum k equals 1 to n of 4k squared over n squared. And then we're going to subtract a second sum, same index, k equals 1 to n, and that one holds 4k over n. And then add a third sum, again, same index, and that one holds the constant 1 at the end there. All right. So now we get to focus on each one of those 3 smaller sums individually. So we're just breaking it down piece by piece here. All right, so let's see what we've got. Still got the stuff out front, our limit and our multiplier, 4 over n. Now in this first sum, okay, notice that there are some constants multiplying our k squared term there. The 4 is a constant multiple, and well, it's really a 1 over n squared if we're thinking of it as a multiplier, but this n squared is also a constant in terms of this summation. So we're going to be able to pull out 4 over n squared from this first sum. Let's do that. Okay, so now we've got our 4 over n squared out front, and then it's just k squared left inside. We're going to basically repeat that process on the next sum. We've got 4 over n that we can pull out. That'll just leave the k inside. So keep that minus sign. 4 over n, and we have our summation with just k inside. And then the last sum here, well, there's just a 1 inside, a constant sitting inside of there, a constant value sitting inside of there. So remember our constant value rule here. Okay, if it's just a constant inside, we can replace this with n times that constant, and that's exactly what we're going to do. Okay, so our constant here is 1, so this is constant value. Okay, and so we get to go n times 1, and that takes the place of that summation. Okay, now let's see what we can do here. Okay, let's rewrite our limits. 4 over n, we got to keep carrying those guys along. Got our 4 over n squared, but now we're going to be able to do something with this right here. This is the sum of the first n squares, okay? And we do have a formula for this. It's not one that we derived in class, but it's one that we have convenient for us that we can use. So that is right down here. This is our formula for the sum of the first n integers squared, first n squares. There we go. So the summation k equals 1 to n of k squared equals n times n plus 1 times 2n plus 1 all over 6. So remember that. You can look up the proof of that if you're interested. Okay, so we're going to go and put that formula into our problem. Okay, so that was n times n plus 1 times 2n plus 1 over 6. And that takes the place of this summation. Okay, no more sum notation there. It gets replaced. And now for our next sum, this is the sum of the first n integers. Okay, that is the little Gauss formula. All right, little Gauss. Okay, so that was the formula that we had derived in class, and that's n times n plus 1 over 2. Okay, and then for our last term, we just have n. All right, so notice now at this stage, we've gotten rid of all the summation notations. There's no more sigmas left in here. So that's a good thing. That shows us that we're making some progress. All right, now let's make some more progress by simplifying what we've got here. So in our first term inside here, here I'll rewrite this actually so that when you're watching this video, you can see the clean copy with those formulas in there. And then we'll do the simplifications on this next line. Okay. Hopefully this video will be helpful for you. Okay, here's our second term. There's little Gauss. There we go. So yeah, now we're going to simplify what we can here. So we can definitely cancel an n out. And we can reduce our fraction here a little bit. 2 goes in twice, 2 goes in 3 times. Okay, so I'll rewrite our simplified terms down below. Okay, so we've still got 2 on top and the n plus 1, 2n plus 1 over 3n down below. Okay, there's not too much else we can do to simplify that right now. All right, second term, cancel the n's for sure, and reduce the fraction. Okay, and we end up with no denominator left, just 2 times n plus 1. And then our little plus n on the end. Okay, so now let's see what we've got here. Okay, we're gonna try to combine terms wherever we can here. So I'm going to start distributing things out so we can see what terms we've really got. Okay, so here we'll have 2 times, distribute this out, that'd be 2n squared plus n plus 2n. So that's 3n plus 1 all over 3n minus 2n minus 2 plus n. Okay, it's a bit of a tedious process, but we do what we gotta do. Okay, let's distribute a little more. Okay, keep carrying those along and distribute here. We'll have 4n squared plus 6n plus 2 over 3n. And then with these terms, we could take the negative 2n plus n. That would be minus n minus 2. All right. Now, let's see. There's a couple approaches we could take here. Let's see. How do we want to go about this? Because really, at this stage, you're doing whatever you can to simplify. So whatever you see first, just go with that. So yeah, as long as it's algebraically sound, we'll end up in the same place, I think. So what I'm seeing first right now is to try and get a common denominator for everything in the brackets. So put everything over 3n. So multiplying this n right here times 3n would give us negative 3n squared. And then multiplying our minus 2 by 3n would give us minus 6n. And then everything can be over 3n. Okay. And hey, that actually lets us do a little more canceling there. 6 n's are gone. And we can combine some n squareds as well. So center that. At our limit, n goes to infinity. Just working this down step by step. Right now we're at n squared plus 2 over 3n. Okay. Hey, that's not too bad. That looks about as reduced as we can get it right now. So let's go ahead and start thinking towards our limit here. Let's bring this 4 over n term back in. All right, so we'll have the limit as n goes to infinity. Multiply these two fractions together. Okay, so multiply the 4 over n times n squared plus 2 over 3n. And that would give us 4 times n squared plus 2 over 3n squared. Okay, we're getting so close, you guys. Limit as n goes to infinity, we'll have 4n squared plus 8 over 3n squared. And we're like right on it now. I'm gonna divide this out just because that helps me see what's going on a little better. You might be able to see what's going to happen with this limit though, because degree of the numerator matches degree of the denominator. All right, but if you divide out, you'd have 4/3 plus 8 over 3n squared. And now we can really see what's going to happen with this. As n gets really, really large, as n goes to infinity, nothing's going to happen to the first term. 4/3 is just going to stay 4/3. But 8 over 3n squared, the denominator on that is going to get really, really huge. And so that second term is going to go to 0. Okay, so we end up with 4/3 plus 0 effectively. And we get 4/3. All right, so remember what we were finding with this before we went through this whole long process? This was to find the integral from -1 to 1 of 2x squared dx. Okay, so that's what this 4/3 is. So integral from -1 to 1 of 2x squared dx. This equals 4/3. But we're not actually done with the problem yet. Because remember, this was an average value problem. So it can be so tempting to just stop when you get here because you're like, I went through all of this work. Aren't I done yet? But we aren't quite done yet because, yeah, remember, we actually need to take that integral and multiply it by 1/2 to get our average value. So we have one tiny last step left here. All right. Then what we're actually looking for, the average value of the function on this interval, is going to be 1/2 of that integral value. So that'd be 1/2 times 4/3. And so we end up getting 2/3 for our final answer. Okay, so that's the average value of the function 2x squared on the interval from -1 to +1. So if we added up all of the infinite little y values in there for that function over that interval, and we added them all up and we divided by however many we added up, an infinite number really. It's kind of hard to think about in that way, but the y values average out to be 2/3 is the overall idea. Okay, so that's where we'll end this. I'll post the notes too.